I'm sorry. I'm a failure.
Okay, so let's talk about the lab from yesterday and this whole buoyancy
Oh
thing.
yeah, we need to go over this.
So,
That was me. I don't sound like that.
I don't know. Well, something about buoyancy just doesn't make sense to me.
Buoyancy is spelled really weird.
it's French.
It is?
Like the word paw. Like that's spelled weird too.
What is?
Paw? I feel like that kind of makes sense.
Yeah, like
P-A-W?
yeah.
As opposed to what, P-A-U-G-H?
Yeah, like no, that's dough.
That's like Prague.
That's ho.
No, that's P-O-U-G-H.
Oh, I thought that's what you just said.
No, I said P-A-U-G-H.
This paper
That's
sucks.
Prague.
How mad would you be if I leave these on? It's like really hard to get them off.
Oh yeah, I need to rip that off.
Do you really want that as I prepare your final?
I already donated to the solar fund.
I got a pair of scissors. All you have to do is cut them off.
Just got on the first day of class.
It's not, I'm not asking you to knock
Yeah, it's on
off
a t-shirt too.
It's so much different if you don't cut them off. That's like,
Sam, be quiet.
Sam.
That comment
I've determined that, do you have older sisters?
yeah, I have one older sister.
She needed to beat you more.
Yeah, you had an
Because
older
I
sister
I
and
grew
you
up with
still.
three older sisters and I was beaten a lot.
Yeah,
So,
Sam doesn't shut his mouth.
I know, that's what I'm telling you, his older sister should have done that more.
Sorry, Sam.
Okay. Anyway, back to our
Not
story.
sorry.
So, here's what you need to understand about buoyancy. And it sounds simple, but yet it's often a struggle. It's rho VH, right?
Right.
What is the density of that represent? The density of the material?
The
Or the
fluid.
density of the fluid? Fantastic. That's the density of the fluid, right? So keep this in mind. This is the density of the fluid. That is the volume that is submerged, okay? And then you have G, right? Because it's the weight of the fluid that is displaced, right? Boom, there you go.
That was for that time.
See, mine's higher and hers is lower.
My
Then
voice is gross right now.
Her
Okay.
voice is lower than mine.
Yeah.
Okay,
I'm gonna eat my apple, so I won't be loud.
okay. Put them there, eating an apple.
Just your chill.
So here's the deal. So on your graph, it was kind of a weird set of units. You had tension, and then you had this area times G times H, okay? So the whole point of this being is that you're not going to change the cross-sectional area, and you're not going to change G. Those are fixed values. So what happens is that as you lower it further and further and further and further into the water, what's going to happen to your buoyant force?
It's gonna go up.
It's going to go up. So this
Wait
is
a minute.
why, when this value is 0, this is why this tension is at a maximum value. As you lower it further and further and further, this line is going to have this negative slope. And what you should see if you do the dimensional analysis, the units of this slope, as weird as this seems, actually works out to be density, which is kilograms per cubic meter. But again, that is the density of the fluid, not the density of the aluminum or the steel, okay? Now, what you should see is that when I look at this graph, so let's say this is your water graph, okay? When I look at this, there should be two distinct lines, one for the steel, one for the aluminum, okay? And then you're going to find the slopes of both lines. In an ideal world, these two slopes would be parallel, okay? Realistically, they're probably not going to be because you only have two data points, okay? So, as you go through this, show me how you found the slope. Then you're going to find the average of those two lines. You're going to use that to calculate your experimental error. Hopefully, what you should see, hopefully, is that this water line slope is around 1,000 kilograms per cubic meter, because that's the density of water, okay? So what I want you to see out of this lab is that when you take that same block and you lower it into methyl alcohol, which has a lower density, that you don't get as much buoyant force, okay? And then that slope is going to be a smaller value because of the fact that you have a smaller buoyant force, even though everything is the same, okay? The AGH values for both, whether you're in methyl alcohol or if you're in water, these values are the same. Same cross-sectional area, same G, same H. The variables come on your tension side, okay? Because as you get less and less and less dense, you have less and less and less buoyancy, therefore you see a smaller and smaller decrease in that tension as you lower it down because of the fact that you have less buoyant force, okay? Cool with that? All right. So everybody's going to be different. Make sure that you show me all those calculations and all that good stuff. When you get to these like conceptual questions, keep in mind what is happening in terms of when you get to like 7, 6, and 7, okay, on those questions. Make sure that you look at this in terms of density equals mass divided by volume. Keep in mind, what are you holding constant? So if you look on that question number 6, object A has a density, object B, okay, if two samples have equal volume, okay? So if they have the same volume, okay, and they're completely submerged, which will have the greater buoyant force, okay? Now, the difference when you get to number 7 is that they have the same mass, okay? So what's going to occupy more volume? The one with the lower density or the one with the higher density, okay? That's going to be a difference in volume. That's going to create the difference in the buoyant force, okay? So keep that in mind when you get to number 7. On that last question, this is going to be somewhat relevant. On the review today, lab had been done on the moon, explain any changes that would occur with the overall results for the density of the fluids change. So here's what I'm looking for there. Ask yourself, if you look at like the density of this baseball, okay? If I go to the moon, am I going to change the density of this baseball? No, but look at what's going to happen on your calculations, okay? Obviously, if I'm holding up something on the moon, it's going to weigh less because there's a weaker gravitational field, okay? But will that impact your bottom line on that x-axis of your AGH? Because, oh, the gravitational is a factor there. So that's what you want to think through. So visualize this. You're on the moon. You're holding up that exact same block, but you're holding it up on the moon. What's going to happen to that initial reading on that Newton scale? What's going to happen to that AGH column on the bottom? What's going to happen to the tension? Keep in mind, what does that graph represent? And is that end product, that overall density of the fluid, dependent upon G? That's what you want to think through, okay? All right. Any questions?
No, sir. Wait,
Bags?
actually,
Bags, you're hesitant. You're like, oh, do I ask? Do I not? I know.
You talked about 3.
We talk about question 3?
Yeah.
Okay. So is that one known as the cylinder?
Yeah.
Okay. I'll give you this hint, right? FB equals rho VG, right? Okay. So you're not going to change the density of the water or the methyl alcohol. You're not going to change G, okay?
Okay.
So you can think of this volume as being the cross-sectional area times the height. So compare the cross-sectional area of that cylinder.
So what?
On this one, okay, you have an aluminum cylinder, diameter 2 centimeters, okay, height of 5 meters. Would the buoyant force be smaller? Okay, here's the deal. So volume is like the cross-sectional area times the height, okay? So you have to find the cross-sectional area of that cylinder and compare that to the cross-sectional area of the block. So if this cross-sectional area here on the cylinder is less than the block, the buoyant force will be less. If the area is bigger, then you're going to be displacing more fluid and you would have a bigger buoyant force. Morella.
Do we have to use the area in our answer? Or could we have reference volume?
Well, if you calculate, if you just went
Can we
straight to the
just
volume
can we use the
calculation.
volume instead?
Huh?
Can we use volume?
Yeah, if you just went straight to volume, it's just easier if you just talk about the cross-sectional area because you're both going to the same height of 3 centimeters.
Okay.
So then you just have to compare the cross-sectional area of the cylinder to the cross-sectional area of the block.
Yeah, that makes sense. Me too. Also, how much is error did we expect?
Usually in this lab, there's usually
Like a
about
lot.
10 to 15% error.
What about 16 to 28? I mean.
Yeah.
I can live with it. The more, I'm just concerned, the problem is you only have 2 data points, so it's tough to get a really good.
Maybe it's the
Line.
ethyl alcohol. Do they have the same mass?
What?
I mean.
No, the densities are basically the same.
Oh.
Okay, anything else?
No.
Going once, going twice, curveball, sold. So get those. So here's what I want. I want the lab itself,
Is that fine?
then I want the answers to the questions, then I want the graphs last. So lab, questions, graphs.
What about pre-lab?
My pre-lab is on the ground.
Well, that's, okay,
Yeah.
if you, excuse me, then we go
So you said
pre-lab, questions, graphs.
somebody showed
Yeah, so pre-lab questions,
Is it okay if mine's pre-lab?
yeah, they're all together.
graph questions?
I just used the regular area the first time.
I need to scan this on my cam scan.
Hey, Siri.
Oh, let me stop this.
Cam
Okay, so the test is gonna be either like all multiple choice or like series of true false questions.
No.
Okay?
What?
Like I will give you a statement, I'm gonna say, which of the following statements are true,
No.
okay?
Hey, one of those are
Those are
mine.
hard.
I know.
What are hard? The true false?
Yours is right here.
Okay, so let's say I give you this problem, and I promise you, you're gonna have a problem. Here's a rocket, make the math easy, it has mass of 1.02 kilograms. The force from the engines is 30 newtons. So I want to find the acceleration, the velocity after 10 seconds. After 10 seconds, we're going to shut off the engine, then I want to figure out how long it's going to take to reach its maximum height. I want to find the change in momentum and the work. I also want to draw a velocity time graph, a force time graph, and a force distance graph.
Oh, yes.
Okay?
Wait, what is the F1 say?
Now, keep in mind this is all multiple choice. All multiple choice.
Force applied.
Okay? Force applied is
Sorry.
30
Can't
newtons.
read.
Multiple choice. So what are you going to do wrong on the screen?
Plug and guess.
You just randomly guess. Valid. It's the beauty of multiple choice, you know. But what are you going to do? What are you going to forget to do?
Find a net.
Graph.
Yeah, that.
Yeah, you're just going to say, oh, F equals ma. You're going to see 30 newtons,
Oh,
and
God.
you're going to see the mass of 1.02 kilograms. And you're going to take 30 newtons and you're going to divide that by 1.02 kilograms, and your calculator will speak to you and give you an answer. And I promise you that's going to be one of the choices. And you're going to go, score! And you're going to feel good about yourself. Okay? And then on Monday, I'm going to give you the test back, and I'm going to go, hey, who did you forget to pay off? Gravity Mafia. But you're going to feel good about yourself on Friday until over the weekend, and you go, man.
No, I'm gonna realize it in AP Bio. Like, oh my God.
Huh?
I always realize what I do wrong in AP Bio. I'm like, oh
Not
my
if we take the
gosh.
final.
So, how are you going to find out how much you have to pay to the Gravity Mafia?
Make a chart.
Huh?
Oh, not that. You would Equals
9.8
mg.
equals mg.
Yeah, find the weight of the opposing force, right? You take 9.02 or 9.8 times 1.02, you get
A number.
negative 10, right? So you have a negative 10 Newton force acting downward, okay? So now, when I take the 30 Newtons and I give $10 to the Gravity Mafia, how much is left? 20. So now if I take 20 Newtons and divide that by 1.02 kilograms, then I get my correct acceleration. Somebody take 20 and divide it by 1.02. 19.6 meters per second squared. Now, how does that play out on my velocity time graph? Slope of my velocity time graph. Okay, so hold on to that thought. So I need to find the velocity after 10 seconds. Okay, so we just said our velocity time graph is going to have it start at 0. It's going to have a slope of 19.6 meters per second squared. And keep in mind what acceleration means. Is acceleration how fast you're going, or the rate at which your velocity changes? Rate at which it changes. It is not how fast you're going. So at the end of, if you start at 0 with that acceleration, at the end of 1 second, how fast are you going? 19.6 meters per second. At the end of 2 seconds, you're going to be going 38.2, okay, 39.2, okay? It's a linear function. That's what that means. Every second that goes by, that's how much your velocity changes, okay? So at the end of 10 seconds, oddly enough, you're going to be going 196 meters per second, okay? Cool. So at this point, I shut off the engines. If I shut off the engines, is there still an upward force making the rocket go up?
Which one?
At the end of 10 seconds, I shut off the rocket engines. Okay? Is there still a force making the rocket go up?
No.
But why does it keep going up?
Because it has to slow down and what's it called before it can change direction.
It has to slow down,
Stop and then before.
speed back up, right?
Yeah.
So what do you call that property of matter that wants it to maintain a constant velocity? Inertia. And what's the only thing that affects inertia? Mass. Okay? So, at that point we're going 196 meters per second. When I reach the maximum height, what's the final velocity going to be? 0. Okay? And what's going to be that acceleration once I shut off the rocket engines? Negative 9.8 meters per second squared. Why? It's the only force left acting on it, right? So if you look at force net equals force applied plus force opposing. You shut off that rocket engine, that's like me throwing this baseball up in the air. As soon as it leaves my hand, it begins to slow down because the only force acting on it is gravity. Okay? And that slope's going to be negative 9.8. So our velocity time graph, I'll draw it out a little bit bigger. So our velocity time graph is going to look something like this. So at the end of 10 seconds, you're going to be going 196 meters per second. Our acceleration here, what was the acceleration? 19.6 meters per second squared, because our force net was 20 newtons. Okay? Cool, right? This point, I shut off the engines. Now, once I shut off the engines, will this graph continue to go up like this?
No.
But the rocket's still going up.
Yeah, but it's.
But it's a
slowing
velocity time graph,
down.
not a position time graph. So then this line is going to begin to slope down like this, right? And what's the slope of that line going to be?
Negative 9.8 meters per second.
Because at this point the net force is negative 10 newtons. So I have to take negative 10 and divide that by the mass. Oddly enough, I get negative 9.8 meters per second squared. Okay, so that's what my velocity time graph is going to look like. Cool. Now, is it at its maximum height at the highest point on my velocity time graph? Or is my velocity time graph going to be at a maximum height when this crosses zero?
Zero.
Because that's when you're going to change the direction, okay? So that's when that's going to be at its maximum height. Okay, that's kind of cool. So we got that one done. So do we have enough information to find the change in the momentum?
Yeah.
What's the initial momentum?
Zero.
Zero.
Yeah.
How do you calculate momentum?
Mass.
Mass times
Velocity.
velocity, right? So my change in momentum, I could write it as P minus P naught, which is probably about as easy as anything to do. So that's going to be my mass, which is 1.02 kilograms, times that velocity of, what do we get, 196 meters per second, minus P naught. My initial momentum is 0, because the rocket started at rest. So somebody take so this is just mass times velocity. So somebody take 1.02 times 196.
200.
Exactly? So 200 Newton seconds, okay? So this is where this becomes full picture. So my momentum time graph is going to go from 0 to 200 Newton seconds in 10 seconds, right? So this is Newton seconds. This is time. What does the slope of a momentum time graph give you? Force. Because it's Newton seconds divided by seconds. Now, here's where the magic happens. If I were to take 200 Newton seconds and divide that by 10 seconds, I would get, wait for it, 20 newtons.
Oh my.
Mike's like, whoa, okay? Because the slope of a momentum time graph gives you net force, okay? Now, you have to pay attention on the test when I'm going to talk about like net force versus just forces. So if I say, hey, I apply a force to a moving bottle of Gatorade, does that mean that the momentum is changing? No, okay? This thing is pushing along at a constant velocity. I'm applying the force, but all the forces add up to equal to 0. So just because you apply a force to an object doesn't necessarily mean that there's going to be a change in momentum or there's going to be a change in the kinetic energy, right? So I give this a push, moving it along. Now, if I stop pushing it, then why does it slow down? There's an unbalanced frictional force, right? Now, if I say a non-zero net force is applied to a moving object, then it's going to accelerate, then the momentum is going to change, then the kinetic energy is going to change, okay? So be very careful when you're reading problems. Is Bergkamp talking about net force, or is he just talking about, hey, I say, hey, you know, Gracie's sitting in her chair. Are there forces acting on Gracie? Yeah. But is her momentum changing? No, because all the forces add up to equal to 0. Okay? Now, if I say, hey, I apply a net force to Gracie, oh, that's a whole new ballgame. Okay? So pay attention to the difference between those two. All right. Now, oddly enough, then I shut off the rocket engines. Okay? What's going to be the final momentum of the rocket when it's at its maximum height? You do not make this difficult. Yeah, because the momentum is going to go to 0 when the rocket is at its maximum height. Okay? So oddly enough, once I shut off the engines, what's going to be the slope of my momentum time graph? What's the only force acting on it when you shut off the rocket engines? Negative 10 newtons. So once I shut off the rocket engines, so I go from a slope of 20 newtons to a slope of Negative 10 newtons, because that's what that represents. Okay, cool with that.
Yes.
Does the area under a momentum time graph have any meaning?
I feel like
Well, look at the units.
no, it's not work. It's force
Okay.
distance.
If you were to find an area, you would take Newton seconds times seconds, and you would get newtons second squared. What's measured in newtons second squared?
Nothing.
Nothing.
Okay.
Okay, so the area underneath a momentum time graph has no meaning, but the slope has a lot of meaning. Okay?
Wait. So force time graph area is momentum. Change of momentum.
Yes. Now, a force time graph.
Yeah.
Don't confuse. Now, if you look at a force time graph, okay, so let's talk about that.
Ouch.
So on a force time graph, I would be applying a net force of 20 newton seconds, or it's 20 newtons, over a time of 10 seconds. Now, if I were to find that area, oddly enough, that area is change in momentum, which is 200 newton seconds. Okay? Now, I shut off the engines. What does that force time graph do as soon as I shut off the engines?
It just becomes negative 10.
Yeah, so that force time graph now shifts down here, and now it becomes negative 10 newtons multiplied by however long it takes to reach its maximum height. Okay? So, on this force time graph, while the engines are being fired, it's a horizontal positive line. When I shut off the engines, then it's a negative horizontal line. Okay, cool with that. What would a force distance graph look like? So let's back up the bus, right? So there's a whole bunch of things that work equals. Work can equal force times distance. It can equal a change in energy, and that change in energy could be a change in kinetic, translational. It could be a change in rotational. It could be a change in UG. It could be a change in us, okay, depending upon the situation. What? Oh. Okay. All right. So, the rocket engines are being fired. That's like me holding this thing in my hand while I throw the baseball, right? Okay. Shutting off the engines is like me letting go of the baseball. So, here's the story. What would this graph, just a general shape of a force distance graph look like? So this rocket engine, while the engines are being fired,
Rectangle.
would it be a horizontal line or it would be a sloping line?
Horizontal.
Horizontal, why?
Because the force isn't changing.
Yeah, you have
Until
a
it
constant amount
stops.
of force, right? Okay. Now, if it was a spring and we were pulling back and launching the rocket with the spring, then if it was a spring, what would the graph look like? That would be a triangle, because the farther you stretch a spring, the more force that takes. So if we're just launching the rocket by pulling back a big massive spring, that would be a sloping line. Fire a constant force from the rocket engines, that's just going to be a horizontal line. Now, let's talk about what this area is going to represent. What's the initial kinetic energy of the rocket?
0.
0, as it's at rest, right?
Yes.
Now, at the end of this time, we know that the kinetic energy equals 1/2 mv squared. So we've got 1/2 times 1.02 kilograms times a velocity of 196 meters per second squared. So somebody take 196 squared multiplied by 1/2 times 1.02.
1.96
You're going to get a big number.
e to the fourth.
Joules. Okay? It's a lot of kinetic energy. Because now, So when you talk about kinetic energy, what's a bigger factor in changing the kinetic energy, mass or the velocity?
Velocity.
Why?
Because it's squared.
Because it's squared. Okay? So what this 1.96 times 10 to the fourth joules represents is the area underneath that graph. Okay? Knowing this, and we know the force is 20 newtons, could we figure out the distance over which the rocket engine is being fired?
Yes. Because
Yes.
you know, yeah. Force distance
Right.
equals what is
Because
it?
that's my work, which is force times distance, right? So I got 1.96 times 10 to the fourth joules. I have to divide that by the net force of 20 newtons. So what do you get?
980.
What'd you get?
980.
980? So that's the distance over which the rocket engine is going to fire. Okay? Cool with that. All right. Speaking of rockets, here's the strange rock that we're on. Here's an orbiting satellite.
I hate this.
I'm just telling you. Okay? So, you have Kepler's third law, TA squared over TB squared equals RA cubed over RB cubed. So what's unique about that equation in terms of units?
Doesn't matter.
Doesn't matter. Why?
They all
cancel
cancel
out.
out.
It's a ratio. Okay, it's a ratio. You're Kepler, you don't have the internet, you don't have a calculator. You want to make this as simple as you possibly can. What's your favorite number if you're Kepler?
1.
1, because that makes the math easy, right? So, this is a ratio. So this means as the planet gets further from the sun, what's going to happen to its orbital period? It's going to increase. The farther out you go, longer the period. So Mercury has an orbital period of 88 days. We have one of 365 because we're further out. Okay, so if you like birthdays, go to Mercury. It's hot, but you have a lot of birthdays because of a birthday every 88 days. Like, oh, birthday, yeah, wow, a day for me. Okay. Drinking age is probably like 60, but that's not here and there. Okay, so then you've got the ramifications of this equation. Little g equals big G m over r squared. One of the most important equations in all of the history of physics, because this explains so many things. Like if I have Hank.
Hank. I miss Hank.
Yeah.
I saw him in the video and I watched it.
Oh yeah?
Yeah.
Okay. So I got Hank and I got Bobby the baseball. Okay? Hank and Bobby the baseball. I dropped them both at the same time. Bobby the baseball and Hank. Which one accelerates faster? Bobby? Hank? Or is it the same?
Trick question.
Same. How does this equation explain the fact that they both have the same acceleration? How could you look at this equation and go, oh, they have the same acceleration?
Because they have the same radius from the, what's it called? Oh, okay.
Well, that's okay. I like, you can go with
Hey,
that.
yeah.
Yeah, you can go with that.
The ratio.
And the mass of the Earth is the same, and so is the big G.
Yeah.
Okay.
So they have the
So,
same little
can
G.
you plug in the mass of Bobby or the
No.
mass of Hank?
No.
So it's the only thing that affects the gravitational acceleration of a dropped object.
The mass of the
How
center.
far you are from the center of the Earth and the mass of the Earth. Okay? Mass of Bobby, mass of Hank, not part of the story. Okay? Does that mean that they both feel the same gravitational force? Which one feels a greater gravitational force?
Hank.
Hank does. So why doesn't Hank fall faster then? Is there more force acting on him? This is the rationale of Aristotle. He goes, look, Hank's heavy, Bobby, not so much. I dropped them. There's a lot more force acting on Hank. Hank should fall faster.
There's more mass
So what?
takes
You're
more
right, there
force
is,
to
but so what?
accelerate it. It takes more force?
Yeah, why?
Force equals MA.
Force equals mass times acceleration. Oh, if I want the same acceleration, as mass gets bigger, I have to have more force. Which one has more inertia? Bobby or Hank? Hank. Hank has more stuff, right? Hank has more stuff. Therefore, it takes more force to get more stuff to move at the same rate, right? So the force is proportional to the mass. Hank has more force, Hank has more mass, he has more stuff to move, but we end up with the same acceleration. Now, keep in mind this is a multiple choice test. Okay, so let's say hypothetically, I ask you to calculate the gravitational acceleration if you're standing on the surface of the moon. Ultimate field trip. Go into the moon. We're going to try and calculate little g. Okay? So what do you need to calculate little g on the moon? Mass of the moon and the radius of the moon. Okay? This is a multiple choice test. Keep this in mind. This is a multiple choice test. What does your answer have to be less than?
That of Earth.
Yeah, let's be less than the Earth's gravitational field, gravitational acceleration, right? Okay? Now, what are the odds that I'm going to give you the radius of the Earth in meters?
Not
Absolutely zero. Okay? Absolutely zero. I'm going to give you that, I'm going to tell you straight up, I'm going to give you that radius in kilometers. What are you going to forget to do? You're going to forget to convert it into meters, you're going to do that math wrong, and you're going to get a value of g that's like something times, that's a really, really, really big number. Okay?
It's
Right?
probably going to be an answer.
So
choice.
when you, since it is a multiple choice test, look at your answers. Go through. Which ones is Burkamp being an absolute jerk and giving us the wrong answers? Okay? It's a multiple choice test. Eliminate the ones that you know are clearly wrong before you even start the calculations.
We do get our big dog equation sheet.
No, you have to have them all memorized.
Oh, okay.
Yeah. And the constants.
Okay.
And the entire periodic table.
Does it hurt?
Oh, this is
She got her
hurt.
belly button
I
pierced.
know, I told him yesterday.
I know. Okay.
That's all the equations, I think. I think that's enough problems.
Orbital period of a satellite. In seconds, what does the exponent have to equal?
3.
The third. It's a multiple choice test. If you don't see a period that's 10 to the third in seconds, guess what?
Wait, orbital period?
Orbital period has to be 10 to the third in seconds.
Or you might be a jerk and give them all in 10 to the third.
I could, but I'm not.
Oh, that's nice.
What about your orbital velocity?
E to the
Times 10 to the
third.
third.
Also has to be 10 to the third. Again, if you're asked to find that, whether it's near Earth orbit, near or lunar orbit, doesn't make any difference. 10 to the third is the
We're
magic
gonna be
number.
nice
Okay?
and only do 1 e to the third.
Huh?
Gonna be nice and only do 1 10 to the third.
I'm not that nice. Okay? I'm not that nice. I like you, but not all that nice. Okay. Let me see what else might be on here.
Is projectile motion on there?
Oh, yeah. So here's how I might like combine some things. So let's say, for example,
Okay, what's this?
you have a book that's frictionless. Huh?
What?
What?
Oh, he finally put grades in.
Yeah, they're like the. I have a 92.6.
Lemmings.
Or leopards. Prey. You know, whatever.
I love
Okay.
lemurs. They're so cute.
So, let's say that I've got a book sitting on a frictionless surface of a certain mass. Call it 1 kilogram. And then I'm going to have that hooked over the end of the pulley, connected to a string. And that mass is also 1 kilogram. So I've got a book, and visualize this. I've got a book up here, frictionless surface sitting on a table. I have another book with the exact same mass suspended from the end of the table. Here are your choices. G is going to be equal to, your acceleration is going to equal G, which is going to be 9.8 meters per second squared. Your acceleration is going to be greater than 9.8 meters per second squared because of the fact that I've got 2 books, therefore twice the force. Or my acceleration is going to be less than 9.8 meters per second squared. Those are your choices, A, B, or C. Those are it. So, how many vote, because it's frictionless and these masses are both the same, that the acceleration is just going to be 9.8 meters per second squared? 1, 2, okay, smattering. How about it's actually going to be faster than 9.8 meters per second squared? Nobody's on the fast train. Okay. Less than 9.8 meters per second squared.
Please don't.
Why? That's the right answer.
I remember this one.
Okay.
Okay, so the book thing that's on the pulley,
The
that's the
book thing
applied.
that's on the pulley.
That's the applied force. So the force net is 9.8 because that is frictionless. But because there's two masses, you have to take the force net divided by the total mass because F equals ma, and then you find your acceleration.
I hope when you work this problem, I see this. Okay. So, yeah, golf clap. Yeah.
Yay!
Yeah. Okay. As a matter of fact, since the mass is doubled, what's the acceleration going to be?
4.9.
It's going to be half that. Because here's the deal. If I just cut the string, what's the acceleration of the mass? 9.8 meters per second squared. So you can think of this as you're going out on a date, okay? And you have to drag along your little brother. So Topher, imagine some of your older sisters go out on a date and they have to bring you. The acceleration is going to be less because they have to bring along Topher. So anytime you're dragging something along, the acceleration has to be less than the acceleration that it would be if you weren't dragging it. Okay? Makes sense.
Yes.
Now, I put this thing on an inclined plane.
Boy.
Okay? Same book. Mass of 1 kilogram. So what are some things that could happen?
It could go down the hill
It could go down the hill. Jack and Jill went down the hill.
Right?
to fetch a
fetch a
bucket
pail
of
of
pail of
physics.
water. Oh,
Oh,
Okay.
it could stay.
So what would have to happen for it to go down the hill?
force parallel would have to be greater than the
And?
force applied by the book.
Yeah.
Yeah.
So this force parallel, okay, if it was greater than the force in the book, it would go down the hill. That's an option. Okay? And how could we increase that force parallel?
By increasing the angle.
Like the angle. Yeah.
As you increase the angle, the force parallel becomes greater.
Yeah.
Is there any way that could happen with equal masses?
No,
Why not?
because it'll never be more than, the cosine, or sorry, the sine will never be more than 1.
Yeah. Okay? So this could never happen where it's accelerating down the hill. Okay? As long as the masses are equal. Just think about this. Let's say you go an extreme case and you put it over a pulley where you have both masses suspended over a pulley. Equal masses. What's going to happen?
Nothing.
Stay constant.
Absolutely nothing. Why?
There's no net force.
Exactly. There's no net force. Okay? What's another option that could happen? It could go up the hill. So what would have to happen to make it go up the hill?
Force
applied is
bigger.
greater.
The applied force is bigger than your force parallel. Okay? So the third option
Stay.
is you can either stay there or move at
Constant.
constant velocity. Now, if it's moving at a constant velocity, what do you know about the applied force versus that force parallel?
They're the same.
They're the same. How do you calculate force parallel? FG sine theta. Okay? Let me see. Let's say that you let go of it and it begins to accelerate. What are the steps involved to calculate that acceleration?
Find the net force.
Find your net force,
And
then
then
what?
you take that divided by the total mass.
Okay, remember, on a problem like this, no matter what, whether it's an incline, an outward machine where you have a pulley system, whatever, to find the acceleration, what do you always divide by?
Total mass.
Total mass of the system. Okay, you always divide by the total mass of the system because of the fact that that is what's happening. You're trying to keep that mass at rest, or you're trying to keep that in motion. Okay? I take a spring and I compress it. It has a certain K value, I don't know, make up a number, 200 newtons per meter, and I compress it a distance of 0.1 meters. What am I doing by compressing it?
Giving it potential energy. I don't know.
I'm giving it what?
Spring energy.
I'm giving it spring energy. I'm giving it us, right?
Us.
And us equals 1/2
Kx squared.
kx squared, right? Am I doing work?
Yes.
Yes.
Yes. Why am I doing work?
Exerting a force over distance.
I'm exerting a force over distance, right?
Yes.
So I have a mass here, boom, I let go of it. Assuming that there's no frictional loss, which there won't be. How does the kinetic energy of that moving object relate to the energy that was stored in that spring?
They're equal.
Equal.
They are equal, because we're assuming that all of the energy that you stored in that spring is going to be converted into kinetic energy. Okay? And then it could go flying off of a cliff. Okay? Compare two things. One block goes flying off the cliff, the other block at the same time falls straight down. One goes off, one goes down. What do they have in common?
Same change in energy, right?
Same acceleration.
Force gravity.
Are they going to have the exact same acceleration when they go flying off
Yes.
the table?
Yeah.
Yeah.
Yes.
Why?
Because.
What's the
thing
only force acting on
is
them once they
gravity.
leave the table?
FG.
Fg. So since they have the only net force is gravity, is their vertical acceleration going to be the same?
Yes.
Yeah.
Yes, vertical acceleration is going to be the same. Okay? So will they land at the same time?
Yeah.
Because what's the only factor that affects how long it takes for something to fall if the initial if your initial vertical velocity is 0?
Acceleration.
You know, there's only two things: your acceleration and
Distance.
well, how far you fall, right?
Oh.
Okay, it's how far you fall and your acceleration due to gravity. That's the only thing. They're both going to have the same acceleration. They're both going to fall the same distance, so they're both going to fall for the same amount of time. Which one's going to have more kinetic energy when it lands? The one that shot off, the one that's dropped straight down, or will they both have the same kinetic energy when they land because they both have the same UG when they're launched?
Shot off.
Why?
Because it
Has a
has
greater speed.
gravitational.
It has UG and
Kinetic energy.
kinetic, and because it has more speed, because it has the speed, therefore it has kinetic energy and
Yes.
potential. So when it lands, that's all going to be more kinetic, so it's going to have more speed.
Yes.
Okay. Gas laws. If there's anything that you need to hammer, how is isothermal different from isobaric, different from isovolumetric? So thermal, that's when it's the curved line. That's when your work is going to be nRT, natural log VI over VF. If you need that equation, I will give it to you. Isobaric is when you use work equals negative P delta V. Isovolumetric, how much work is done on isovolumetric systems?
0.
0. Why?
Volume is the same.
There is no change in volume. That's the only one that's a vertical line. Okay? You have to be careful on signs. So this is how this would play out. I would say a gas does 400 joules of work while absorbing 200 joules of energy. Okay? What's the value of delta U? So it's either 600, positive 200, or negative 200. So here's your choices. 600, negative 200 joules, positive 200 joules for the value of delta U.
Are we voting? Or
So here's A, here's B, here's C. So here's the situation. So a gas does 400 joules of work while absorbing 200 joules of energy. Okay? So here's your choices for delta U. 600, negative 200, positive 200. Okay? So how many vote, how many are on the 600 train? One? Sam's on the 600 train.
I don't want to be on the 600
Nope,
train.
too late.
anymore.
No, you already bought your ticket.
The door's closed.
Am I in the train?
You're on the train.
I'm already on the train.
We're doing work.
Oh no.
How about negative 200 joules? A lot of people on the B train. What about C, the positive 200 joules? Nobody's on the C train. So why are the vast majority of you on the B train?
because work is negative.
Why is the work negative?
Because the gas is doing the work, which means it's exerting energy and losing it.
It's true. Since it's doing work, this is like Nikki B is wrapped in saran wrap and Nikki B hates being wrapped in saran wrap. So he's going to do work against it. What's the only way I can make that answer 600?
If the
We're
gas
both
is
was done on.
works-
Yeah, if we compressed the gas and dumped energy into it at the same time. That would give that gas a tremendous increase in energy because you're dumping energy into it and you're compressing it. So that would be like me taking all of you, we're gonna turn up the thermostat to like 90, and I'm gonna make you all stand really close together.
Oh,
So what's gonna happen to the internal energy of all of you?
gonna
It's gonna
increase.
go up, okay? Because you're going, this really sucks, okay? Nikki B,
You can wrap me in saran wrap. So that
I'm
you
not.
got it.
That's
Have you
no.
been wrapped in saran wrap?
No.
Oh.
But we're
Anything
not.
for
We're not
saran
going down
I
that
was
road.
gonna say, I was like, you should duct tape yourself to the wall for the solar project.
Why?
That'd be funny.
I would duct tape myself to the wall.
Well, we could raise money.
Yeah, to raise money.
You're there for the entire day.
No,
One school day.
no.
One hallway.
We
to
feed
one.
you.
Oh, great. You'd feed me.
You give a lecture.
I'm like a caged animal. We'd feed you. Oh, gee, thanks.
That's funny.
About how
Okay.
many new people you meet.
You can make the door and then we can open it.
What are factors that affect the moment of inertia of a spinning object?
the
The radius.
gas.
And the radius, right?
Yes.
So, is that the radius of the outside circle or the radius in terms of the distribution of mass? Distribution of mass, okay? Torque equals two things. What does torque equal? Force times radius and
I fish.
I fish, okay? L equals
W.
I, what?
I omega.
I omega, right?
W.
Does angular momentum have to be conserved?
Yes.
So if I'm spinning and I bring my arms in, what's going to happen?
You're going faster.
I'm going to go faster. Why?
Because your moment of inertia is smaller.
That's right. If I bring my arms in, I decrease my value of I, therefore to produce the same value of L,
You have to increase your angular.
I have to spin faster. If I put my arms back out, I have to slow down. You deploy a satellite,
Right.
and it oddly enough has solar panels to generate electricity. As soon as you deploy those solar panels, what's going to happen to the rate of spin?
It's because your
It's
eye
going to become
decreases.
smaller. Okay,
Your eye decreases.
So,
angular momentum.
let's chit chat about what you have
Yeah.
for the
Your
review.
velocity. Your angular velocity will increase.
So, first page, here are the big topics. Okay, what I fear most is the planetary motion stuff. Okay, just down there. There's that. This is just all the topics. This one is the solutions to, these are separate. So this is, let's start, bring the curtain down. So here are 36 questions, and this is the whole gamut, okay? This one that goes with this is everything from the beginning of time up to now, okay? Like, seriously, we have rockets, we have
Dinosaurs.
different graphs, we have pressure volume graphs, we have buoyancy, we have the whole smash.
How many
Okay.
questions are on the test?
Huh?
How many questions are on the
I
test
don't know.
again?
I don't know.
A range?
Okay.
You're still making it?
Oh, I always do.
Oh.
Now, this one is just thermodynamics and buoyancy, okay? So if you're just worried about that, you might focus on this one, because this is just the thermodynamic and buoyancy. The other one has everything. So here's a new record. Question 2 has parts A through O. Okay? A through O, that's a new record.
I should
So-
just be like, I'm not coming.
Anyway, so this one is all stapled together. It's the questions and the solutions all together. So, can you give everybody one of those?
Yeah, I'm calling it a
Bro, I have to work. I called in on Tuesday.
I called it on Tuesday too.
I know, but I'm at 4 points right now. We can only have 5.
When does it reset?
The 19th. 4 days from now.
I don't think it's your fifth one.
How many points can you have?
5. And, well, 5 and you get like considered to be fired.
Weird, bro.
No, I never called it.
No, that's important.
If I did, I don't know.